Hello, I'm Nguyen Viet Khoi from NAVIS Center, SOICT, Hanoi University of Science and Technology, Vietnam. Today I'm gonna give a presentation about our website NaviNet, which monitors phase scintillation in real time using CORS network, a network of continuously operating reference stations. So first, let me briefly introduce our research group, NAVIS Center. The NAVIS Center was established with a project co-funded by the European Union through the collaboration among European and Asian partners. Here we focus on research and development of satellite navigation technology, especially in Southeast Asia. We've been being supported by international institutions such as the Politecnico di Torino, or Polito, from Italy, and the Polytechnic University of Catalunya, or UPC, from Spain, with collaborating partners such as NAVSAS and GAGE. The NAVIS Center is located in Hanoi, Vietnam, just above the magnetic equator. This place has great opportunities for studying the ionosphere and its irregularities, known as ionospheric scintillation. So, what is ionospheric scintillation? We all know that GNSS signals are transferred through the atmosphere. The ionosphere is the upper part. It contains sufficient ions and free electrons to produce some impact on the propagation speed of the GNSS electromagnetic signals. The effect depends on its electron density, which is typically driven by two main processes. During the day, sun radiation causes ionization of neutral atoms, producing free electrons and ions. During the night, the recombination process prevails, where free electrons are recombined with ions to produce neutral particles, which leads to a reduction in the electron density. As you can see in the plot depicting the standard deviation of the carrier phase and corresponding fluctuation of the ionospheric effect on it. Without scintillation, regular electrons gradually refract GNSS signals. This refraction depends on the frequency and can be eliminated by dual frequency receivers. But under scintillation, irregularities of the electron distribution refract and diffract GNSS signals, causing significant fluctuations in the amplitude and the carrier phase measurements, or even losses of lock in the tracking loop. And then finally, the problem is that the accuracy and availability of the service decrease. A carrier phase measurement is a sum of the true distance from a satellite to the receiver plus some errors. Some of the errors can be modeled, such as satellite orbiting clock, the solar tide, the total group delay, the antenna effect, the wind-up effect, and the tropospheric delay. They can be corrected at high accuracy. The unknown errors are the receiver clock bias, the integer number of carrier cycles, and the ionospheric effects, refraction and diffraction. The refraction is proportional to the inverse squared frequency, so we can remove it with a receiver working at two frequencies by using the ionosphere-free combination of two measurements at those two frequencies. But unfortunately, the diffraction cannot be removed by this. The refractive scintillation happens at both high and low latitudes, but the diffractive scintillation is remarkable at low latitudes. Remarkable diffraction can cause large noise in the measurements, losses of tracking lock, and cycle slips, which the solution of the integer number of cycles needs. So we need some indicators to monitor this phenomenon in real time. Currently, the amplitude scintillation index S4 and the phase scintillation index sigma phi are provided by a special type of receiver, ISMR. ISMR has a highly stable clock to draw out the fluctuation of the ionospheric effect. These special receivers are not so common. Meanwhile, conventional receivers from a CORS network, a continuously operating reference station network, such as IGS Network, are widely distributed over the world. And we have proposed a method to compute the phase scintillation index sigma phi for receivers of those well-distributed stations. First, we remove the modelable errors, and then the receiver clock bias, and finally the cycle slips correction. The wide distribution of stations and IGS real-time streaming services help us create a website to monitor the scintillation indices in real time. The real-time services of IGS provide us the precise orbits and clocks of all satellites. These data are streamed in RTCM3 format through an internet protocol, which is called NTRIP. The NTRIP caster is located at products.igs-ip.net. We also use this NTRIP to collect the code and carrier phase measurements of the target station. Stations from IGS broadcast data at igs-ip.net, while non-IGS ones can use our NTRIP service. Our server gathers the data and computes the required scintillation index and sends it to the website, where clients can view it in real time, as well as the sky plot of the target station. The correctness of our method is proved in our previous research with post-processing data. Our results are close to the ones provided by the special ISMR, which can point out the scintillation occurrence. And now we're going to a video displaying our website, NaviNet, and then we can see how we show the indices to the clients. Now let's have a look at our website, NaviNet. First, we select the indices, and then the two frequencies, the station, and click Start. So in the plot, we will see the two indices of station SIN1 in Singapore. ROTI, or rate of total electron content index, is plotted at the bottom plot, and sigma phi 1, the phase scintillation index at frequency 1, is depicted on the upper plot. As we can see in the sky plot, all satellites in view from the station are depicted. Here we can see that there's no scintillation. The indices are not high. Normally, scintillation should be greater than 0.2 radian. Now we stop and change to another station. In the lower plot, we will depict another index, which is the residuals of the ionosphere free combination, and from this we can see the variation of the receiver clock. This is what we do in our method. to remove the receiver clock fluctuation, to isolate the fluctuation of the ionospheric delay, and then we can get the standard deviation of it, which is the sigma phi as depicted on the upper plot. All the plots are in real time, so I've introduced you our website NAVINet, which can monitor the phase scintillation index sigma phi in real time from many stations over the world. The requirement for the station is it can collect data in real time and send it through N-trip connection, which is normally featured in a CORS network. Our service has been being developed for multiple GNSS. We're looking forward to more results in the near future under the multi-GNSS environment. So thank you for listening to my brief introduction of our website.